Alright people, it's that time again. The time where we're going to master our algebra. So it's questions 17 to 27, your 10 question installment. And if you're interested in getting those answers without having to go through the video, then go over to Patreon, and by the end of this series, all of the question answers will be in one document that you can get from there, okay? Alright, question 17. Hopefully we know that all numbers are written in columns. So we've got our decimal point, which might be here. Then this would represent our units, this our tens, this our hundreds, etc. And down here our tenths, 100ths, and 1,000ths. And this continues. This is something that you would have learnt and dealt with in primary school. And here it is, back to haunt you. So how do we translate this? Well, if I talk about how many I have of each, then I have 8/10ths in there. But because I've got a whole thing going on here, I would say I've got 832 thousandths. So this on its own would be 2 thousandths. This here would be 32 thousandths, if we get rid of that barrier, 32 thousandths. And then we get rid of that one, it'd be 832 thousandths. What we're looking to do is understand that the last one, so that's this one here, the last is what defines it. So in our case of 0.375, we have the final digit in the 1,000ths column, and we might write that like this. And so what we have is 375 1,000ths, and that's how we write the fraction. That's how we say it. The amount that we have is on top, the numerator, and the denominator tells us what exactly the split is. So we split 1 into 1,000 parts, and we've got 375 of those in this question. The reciprocal is a very important concept, as we've already seen. This time we're going to see it with algebra. We were looking at the number that we multiply it by to get to 1, and we found that flipping it was always needed, and it's the same with algebra. So the reciprocal of 3x over 4 is 4 over 3x. Okay, order small to large. In order to compare apples with apples, all of these fractions need to have the same denominator, just like when we're adding or taking away. So our first job is to convert, but we need to think of a common multiple, so like a global common multiple, or maybe just the lowest common multiple of, say, 12, 3, and 24. Okay, and you've probably seen that it's 24, because in the 12, 3, and 24 times table, that's 24 is in them. We have the LCM of these as 24. Okay, now we're aiming for 24. We are going to change. Now this one needs to multiply by 2, but we do the same to the top as well. Okay, you can't just go changing the bottom without the top, because it doesn't stay the same. 3 is going to have to multiply by 8, same on top, and 24 is going to stay the same. Do the change underneath. So top times 2, which is 10, bottom times 2, 24, just like we wanted. 8 times, we'll do the top first. 8 times 1, 8. 8 times 3, 24. And the last one, it stays the same. And looking at that, we can see how many of the 24ths we have. Down here, we've got 10 24ths, 8 24ths, and 7. So it's just a matter of writing them in order now. But I wonder if people will make the mistake. So have a go. Write them in order. And it says from smallest to largest. So here's from small to large. So it's the one here first. So far, so good. Some convention says that we write an inequality in between, but you don't have to. You could write a comma. The next one is this one. And I want to know if you wrote this or you wrote 8 over 24. Because the question says to write these numbers in order, not the ones that we converted it to. And then lastly, 5/12. All right, there you have it. The lowest common denominator of 2/9 and 5/12. Well, this is just looking at denominators, the 9 and the 12th. Okay, so we don't actually need to go ahead and do anything else. But a denominator is the thing on the bottom, right? So we're just looking for the lowest common denominator that these two could have. If we're talking equivalent fractions, you know you can multiply the top and the bottom by the same number. And so there's a whole infinite range of different fractions that could be written instead of these ones. Fractions that would have the same denominator. That's what common means. So the question really here is, if you did multiply these fractions by whatever you wanted to, then what would it be such that it was the smallest number where the bottom two denominators are the same? So I'll give you an example. If I times this by 2, I've got 24 over 5. I actually can't get to 24 with 9, but let's say I times this by 3. I've got 27 and 6. Well, that's an example where they're not the same. That's not a common denominator. They're different. I need to change the top actually as well, so don't forget that. But these are now the same fraction, okay, but written with different numbers. But they've not got that common denominator that I was looking for. All right, so what could we multiply by? Because I've tried 2 and 3, because if I did 2 and 2, it would still be different. But you could probably not have to do it by guessing. This would be a longer time, perhaps. The best way to find a common denominator of 9 and 12 is asking what is the LCM. These numbers are pretty small, and you could go up in your 9 times table or the 12 times table until you get to a number that fits with 9. For example, 9, 18, 27, 36, and 12, 24, 36. And you think, okay, well, that's the lowest common multiple because these are the multiples, and the 36 is the first one that they're the same. What happens when these numbers are huge, like 890 and 77? What's the lowest common multiple? Well, the method that works really cool is to break them down into prime factors. So there's your prime factors again. 9 is 3 times 3, and 12 is 3 times 2 times 2. And looking at where these overlap, it's really useful. So we draw a Venn diagram for this overlap. So this circle here represents the 9, and the right-hand side circle represents the 12, and then there's an overlap. So the overlap is for the numbers that are in both. So I can see a 3 is in both, so I'll put 3 in the middle there. And then what's only in 9? Like that's not in both, we've got a 3 left over. That's this 3 here. And what's in the right-hand side is 2 times 2, which you could say was 4. And that comes from these 2 here that's left over. Now, what we're looking at is prime numbers in a very specific order. This number in the middle is actually really special. This here is my highest common factor, is the number that will go into both 9 and 12. And it's the biggest one that does that. So as you can see and agree, it's probably 3. Now the most important thing to us is where we multiply these together, and these are the LCM. So off to the side here, perhaps, we have 3 times 3 times 2. And why do we have to do the Venn diagram? Well, it just doesn't count the 3 twice. If we'd have done it up here, we'd have done an extra 3. And what it needs is to count just once to get the lowest. So this is our LCM. So 3 times 2 is 9 times 4, that's 36. We knew it was 36 anyway, so that's reassuring. And we can see that this method works. So if you're ever unsure about the LCM, you can write out the products of primes, and then you're going to see the overlaps. Once you've got the overlaps counted just once, you multiply them all together and you've got your LCM. We confirm that it's 36. So coming over here, we have the lowest common denominator as 36. And obviously, if we were going on to use that to add these fractions together, you would multiply this one by 4, and you multiply this one by 3, and that would get you your 36. And you could go and add them, take them away, or just compare them to see that that is bigger than that. Okay? We're going to get rid of that because that's not the point. That was the question. Now we come to simplify. We can only simplify if terms are like terms. So I get the benefit of using a color here. Like terms are where we have a certain amount of a term which is like, and that sounds really odd, but typically it's either a number with a number or a letter with a letter. And if we had a letter squared, that's different from a letter on its own. That kind of makes sense, doesn't it? In some cases, it's true. Like if you had 1, then 1 squared equals 1. So it's not always true in that regard, but in this case, we don't know that it's 1. And so if you have an x squared, it's not the same as an x. So here I like to call them different families. So an x is one family, a y is a different one. So x's and y's don't mix. X squareds don't mix with either of those. Same as x cubes, they don't mix. The numbers are another. So we've got the number 7 there, but it's not looking too neat. And we've got a number of different ones as they prop up. Interestingly, combinations are unique. So if we had xy, that's also different from any of those. And not, however, different from yx, because they are just written in the other way around. And as we know, with multiplication, you can write them either way. It's commutative. So now we've been introduced to all these families, we can see that the x's are the show here. This is an x term. There's 5 of them. There's an x term. There's 7 of them. And here is, well, we're going to give away 2 x's there. So it simply becomes 5 plus 7 minus 2. That's the sum that you're doing. And that's how many x's there are. you'll notice that we can factorize the x out and it looks like this. And so here's a new term for us in this course. If there's something that's multiplying a variable, then that's called a coefficient. Let's write that down at the side. In fact, let's move that up there. It's called a coefficient. Okay, and there's another coefficient. Interestingly, some people might think that that's 5, 7, and 2, but it's actually -2. It's -2. Okay, so you have to include the sign in front, and 5 out the front there doesn't have one because it's just positive. All right, so in this regard, we've got 5, 1, 2, 3, 4, 5. Then we've got 7, 1, 2, 3, 4, 5, 6, 7. And then we're going to take away 2. So maybe we could call that like give away 2. So in total, we've got 5 plus 7, which is 12x. And then we're going to take away 2x. Okay, and that's going to give us 10x's. Now, if you want to be totally like transparent here, whenever you've got a number in front of an x, like 5x, you're essentially doing an addition. We saw that earlier. So x plus x plus x plus x. That's what that looks like. And it's kind of symbolic of those circles that I drew. I will do this. Watch this. We're going to also add the 7x from here. So that's 1, 2, 3, 4, 5, 6, 7. And then we're going to take away 2x. So we're going to take away x, take away x. So this is a very interesting tally, right? So it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we go backwards, 11, 10. So that's like how we write it out. I can't stress that that's enough about how important that is to know. That I'll just write it again. 3x is x plus x plus x. And if you had x cubed, like the little number at the top right, that's x times x times x. This is a really important fact to write down in a poster somewhere, because it's a fundamental concept. I'm going to get rid of it because you can always pause the video. Right, now we're going to roll with the like terms. You can see that this here is a squared, and this is a squared, and this is a squared. They're all in the same family. So that means we just add the coefficients. Now I'm going to do it a little bit quicker this time. I'm just going to write the coefficients at the front as 4 plus 3 minus 5. That's how many a squared I have. And this way of seeing it is really useful. I've seen it in algebra quite a lot at the higher levels past GCSE. And it's essentially factorizing, but this is what you can do because that's the focus. 4 plus 3 is 7, take away 5 is 2a squared. And then we've got this question 23. What I like about this is it's like a tricky, we've got xy and an xy, cool. But then we've got a yx. And as you can see, that can be off-putting. But x times y is the same as y times x. So these are all like terms. Some people, that might be you, like to write again with the correct order. And that's alphabetical order for a start. But now we can see that they are like terms. We have 2 plus 3, take away 1. And that's another learning point, I suppose. Did you get caught out there? So when we're looking over here, you can see there's no coefficient, right? I'll highlight the coefficients here. That's 2, 3, and, oh, where is it? Well, if you want, you could also be that kind of person that writes a 1 there, because if it was 0, there wouldn't be anything there at all. So it can't be 0. And if there was a number like 2, you'd have to put it. The only number that can be there is 1, and we generally don't write 1. So just don't forget that it is 1. 2 plus 3 is 5, and take away 1 is 4, lots of x, y. Now, do we have the same down here for question 24? We've got A, B, C. And yes, we've got A, B, C, but in a different order. So they're all A, B, C. They're the same family. So we've got 6, take away 2, plus 1. Okay, at the front there. And that's all A, B, C's. So that's 4 plus 1, which is 5, A, B, C. Number 25. Simplify. Okay, now we've finally got different terms here. So we've got our x squareds. And if you can't use a color, it's easy. You're just going to underline the like terms, okay? It's a little bit more ugly, but that's fine. So we've got x squareds here, we've got x squared there, and we've also got the family of x's. Nice. So let's deal with the x squareds first. We've got 3 minus 1 x squareds. And then with the x's, we're going to add them together because there are two distinct groups here that no matter what there is, they're together here in an expression, so they're being added together. 2 plus 4, lots of x's, because you could draw it out. Maybe it's something I'll do. So x squared are represented by a triangle, say. We've got 3x squareds there. And then we've got minus x squared there, so we'll draw it in red. And then for the x's, we'll do circles. There was more of them, so I thought I'd go with circles. They're easier to draw. 1, 2, 3, 4. So essentially, you can add them up this way. And the sum 3 minus 1 is represented here. And 2 plus 4 is represented here. All right, let's finish this. 3 take over 1 is 2x squared, and 2 plus 4 is 6x. So we're playing here. We're simplifying. It is real-life quantities, right? We don't know what x and x squared are going to be, but it is as simple as adding up a certain number or a certain family and seeing how many there are. But sometimes they have horrible negatives in, so let's have a go. Here we've got x's, and welcome to a new type of family, the numbers. Okay, so they're just their own family. So we have a minus, and remember it can't be 0, it can't be a number bigger than 1, so that's a minus 1 in front of that one, and a plus 4 in front of that x, and that's how many x's we have. Remember, these here are called the what? Begins with C. Coefficients. Yeah. So these are all we need to evaluate when we are adding these up, are coefficients. And because there's nothing else, there's no other number, we have to leave it as it is. Because it cannot combine with this family, it's a different family. This looks a bit annoying. Nobody wants to start off with a negative number. So because you're adding these two numbers together, it's also commutative. You can add them in different orders. So it's actually sometimes better to write it like this. 4 minus 1x minus 6. And you can just switch them around. So really cool. 4 take away 1 is 3x. You see how that's so much easier? 4 take away 1 rather than minus 1 plus 4. Something easier about that. Okay, there we go. 3x subtract 6. And our last one for today is MNP, and MNP. Yes, they're all the same. So just double checking. 7 take away 3 plus 2. And that's in alphabetical order, MNP, LMNOP, if you have the alphabet. But 7 take away 3 is 4 plus 2, which is 6 MNP. And they're all being multiplied together. And there's your final answer there. So thanks for coming along to this particular episode. We've got some basic skills in the background, and some algebra has crept in finally. We're going to be looking at some more difficult stuff as we go through. As you can see, these levels go from level 1 to 3. And call it a nice easy week. You don't always have to be flat out. Everything we see in these questions are an important concept, and you're going to get there. Just stick with it. All right, I'll see you next week for the next one.